All right, it's 8 p.m. GMT. Hello, everybody. Thank you for joining. And sorry for the very late reminder about this talk. But nevertheless, thank you for coming. And I'm very happy to host today Nicolas Menet from ETH Zurich. So without any further delays, Nicolas, the floor is yours. Please go on.
All right, thank you for the introduction. And I'm delighted to be here at VSAONLINE, of course. All right, so in this presentation, we will discuss MIMONETs, multiple inputs, multiple output neural networks that exploit computation in superposition, which is a paper that we presented at this winter's NeurIPS conference. Okay. While I could torture you with a bunch of evidence on recent trends in machine learning, the basic direction of the field is actually quite simple. The training time, the size of the training data, the number of parameters employed in the model, and with that also the floating point operations that are required at inference have all gone through the roof in recent time. Now with that come engineering challenges, but also opportunities to tackle the inefficiencies of neural networks. Now, there are already a bunch of different approaches on tackling the last point, which is what we're going to focus on in this talk, namely reducing computation complexity at inference. And I'm just going to recap some of them. There's knowledge distillation, where you train a large overparameterized model, which you then distill into a smaller model by teacher-student training, such that the small model mimics the large model, which was easier to train. There's also the approach of using neural architecture search, where you try to find the most performing architecture without blowing up too much the size of the model. Now, part of that is are also techniques such as low-rank decompositions, which were most famously used in the MobileNet architecture with depth-wise separable convolutions. But they've also been recently used in transformer architectures with stuff like butterfly or monarch decompositions, where you take a matrix and just decompose it into two low-rank matrices. And you hope that with this much cheaper computation, you still get a high accuracy. Finally, there's also approaches where you insert sparsity into the network by pruning network weights, which then mean, of course, less computations, albeit at the cost of a more involved multiplication procedure because you have sparse multiplications. And finally, there's also quantization, where you don't reduce the number of flops, but you just make them cheaper by switching to a low fidelity representation of weights and activations and weights. Okay, so what we're going to propose is something new. We're going to compute in superposition in a neural network, which means you're going to have multiple inputs that we're going to pass through the network at once in one pass. And thus, the floating point operations per input gets divided by essentially by the number of superposition channels that we use. And it's important to note that this computation superposition can also be combined with the other approaches in order to reach some synergy or best operating point. Okay, so MIMONETs are well known in the telecommunication area, where you have a transmitter with multiple antenna and a receiver which also has multiple antenna. And you try to send multiple data packets, but they interfere with each other. So the receiver sort of has to undo what the physical channel, all the scrambling that physical channel introduced. Now we're going to use this concept, but we're going to insert a deep neural network in the center, which is going to replace the physical channel. And we're going to try to put in multiple inputs at the same time and get multiple outputs at the end of it. So let's look at the architectural diagram. So what we're going to do is we're going to have multiple inputs, here shown as some images as an example, and we're going to superpose them by element-wise addition, which in VSA parlance is going to be our bundling operation. Now you may notice that due to commutativity of addition, the intermediate output of the superposition is invariant to the order of the inputs. So even if the deep neural network is able to produce the desired outputs for each of the inputs, you do not know how to assign it to the different inputs channels. So already for that reason, it's important to introduce some labeling or some binding operation where those inputs are bound with keys, either random or trainable keys, before being superposed, such that we can trace back which input it came from. Now, an additional benefit of this binding is that the binding orthogonalizes the inputs. And since they become orthogonal, they interfere less in the deep neural network, and we get better outputs. Okay, so what happens after applying the deep neural network? Well, we need to unbind. We need to have a matching unbinding operation where from this shared representation, we get back just, we can isolate one of the information. And after this unbinding operation, we're going to apply the fully connected layer to each unbound representation separately. This is just the last layer of the network, which in our case is going to be a classification layer. Now, the reason for applying this fully connected layer not in superposition is because it provides a natural cleanup. So here you can see a bunch of values which are superposed and bound with these A keys. Now, if we apply unbinding, matching to some key to this superposition representation, then if this unbinding operation is linear, it's just being applied to each element separately, and it actually retrieves our desired vector xk, our value vector. But additionally to this retrieved vector, we get another noise vector, and this stems from the residual when binding and unbinding with non-matching keys. And this noise vector is just going to look into some random direction. It's going to have a much larger magnitude than xk because it has much more terms involved in it, but it's going to look into some random direction. Now that's an issue. We have to somehow get rid of this noise vector. And the nice thing about this last fully connected layer for classification is that it can get rid of this noise. Essentially, you can think of each logit at the end as an inner product with some of those weight vectors from the weight matrix in the fully connected layer. And these inner products, this inner product, because it's linear, it's going to be decomposed into an inner product with our desired value xk plus inner product with the noise of some vector defined by these w's, which is associated to this class of the logit. Now, because random vectors in high-dimensional spaces are orthogonal, the inner product between the logit vector and the noise is going to vanish, even if the noise is fairly large. And consequently, we're just going to be left with the inner product with xk. That's why we apply the last layer separately after the unbinding. Now, let's look a bit more closely at the binding operation. The binding operation naturally also depends a bit on the exact architecture that we use. So now we're just going to look a bit more closely as a first example at how we implement binding for CNNs. Now, CNNs have two vital properties. Firstly, the CNN as a whole is a translation invariant mapping. And this is implemented by having each intermediate layer being translation equivariant and with a global pooling at the end. Translation equivariance essentially means that if you have an input and you apply this convolution on it, or maybe also some activation function, and you shift this input, then the output is just also going to be shifted. And that's super useful because it introduces an inductive bias into the network. A translation invariant map, or if we already have given that the map is in translation invariant, then the network doesn't have to learn that salamander to the bottom left is still a salamander if it's being moved to the top right. It just knows that. So this leads to a much lower sample complexity and is important for many use cases of CNNs. Now, the second property of CNNs, which is going to be important to think about our binding operation is that we do not convolve with convolutional filters of unbounded support. They're always small. They're maybe like these 3x3 filters. And this is super useful for CNNs because it drastically decreases the complexity when running the CNN of inference. So what we really want from a binding method is, on one hand, it should not destroy this inductive bias of translation invariance, and hence it should be translation equivariant. And secondly, it should not scramble the information of our input tensors all over the tensor, such that we could no longer use local filters. And this naturally leads to a new binding mechanism, which we call position-wise HRR binding. Essentially, we apply some binding mechanism. In this case, we choose HRR, which is like this circular convolution with some trainable or random vector. But we apply it at each position separately, always with the same key, the same binding vector. This both keeps the information local at some position, but it also, because we always use the same key, it also leads to a translation equivariant operation, and hence we get these two properties. Okay, so we now have this new binding mechanism. You may be worried that since we now bind only in this essentially three-dimensional space, because images have like 3 channels, we are not in high measure computing, and the nice properties of like quasi-orthogonality of random vectors no longer apply. So to get back into this realm, we actually also apply the first layer of the network separately to each input to decrease the spatial resolution, but increase the number of channels or feature maps of the network. And thus we get more into this high measure computing realm. Also, it's important to note that the accuracy drastically increases if we use CNNs with a lot of channels, a lot of feature maps. And later on, we're going to talk a bit about wide ResNets, which have like this high width, because then we get this high dimensional computing regime where vectors are, where you have more space for computing in superposition due to orthogonality in high dimensional computing. Okay, as a summary, we use real valued key representation, which is useful for differentiability. And for binding, we use this position-wise HRR method with either trainable or frozen keys. Both work equally well. Now, for unbinding, we actually use a different VSA framework. Because the deep neural network is highly nonlinear, we cannot accept to be able to use some sort of a very similar method for unbinding as with binding, because it transforms the whole thing in an unpredictable fashion. So what we use instead is MBAT, matrix binding of additive terms, where we just unbind with trainable matrices, thus using sort of the most flexible method to unbind in the network. Okay, now let's look a bit more closely at this issue of computing in superposition through a map which is highly nonlinear. Because although we are able to put our inputs into these protected subspaces, the issue of nonlinear maps is that they, after applying this map, they may no longer be protected. They, at some point, may no longer be orthogonal, and thus we're not going to be able to retrieve the objects. So how are we going to design an architecture that's sort of able to keep this in the product, being in the product preserving, but still being able to compute nonlinear maps? Well, there's an unfortunate theorem that if you are exactly in the product preserving, then if a map is exactly in the product preserving, then it is both linear and an isometry. So it's going to be in a product, it's going to be essentially a rotation with maybe some reflections in it. And that's hard enough for deep neural networks. It's not enough representation power. So what we're going to do is we're going to somewhat induce an architecture that's able to strike a balance where the network can easily choose how isometric it wants to be and choose between being fully isometric or having nonlinearities where it actually needs them. So the first architecture choice is to adopt ResNets. ResNets have this residual connection with an additional residual block, which is like this blue thing here. Now we're going to scale it by some parameter alpha, which is just going to indicate like the global scaling of this residual connection, and which can easily be selected by the network by just downscaling the weights. So let's look at the inner product between the outputs of this one layer for two different inputs, x and y. Now by linearity of the inner product, we can expand this term, and if you assume that the inputs started off orthogonal in the first place, this first term cancels, and we get this term linear in alpha and linear in alpha squared, which, if the residual connection is small, if the network chooses small weights, these two other terms vanish fairly quickly. So this makes it much easier for the network to sort of choose how isometry preserving it wants to be, and doesn't have to sort of optimize some complicated function for this very important choice. Okay, now the second thing we're going to do is we're going to regularize the convolutional layer. Now you all know that, well, we just said that in the product preserving maps are essentially unitaries. They're just rotation through reflections. And unitaries are characterized by UTU being equal to the identity, which is equivalent to the Frobenius norm of UTU minus identity being equal to 0. In a very similar way, we can derive a regularization term for our convolutional layer, where here this convolution is essentially just the convolution where once we consider the matrix A, which is I guess the weights, we once consider them as weights and once as inputs. And to derive this delta is like this Kronecker delta function, which mimics this identity. And this is equal to 0 exactly if we have an inner product preserving convolution. And with this term, we can sort of have an easier optimization process in the network, and we can sort of force it to already consider isometry preservation right from the start. Finally, we have the activation function, which must be nonlinear for the network to have universal approximation theorem properties. But instead of having a fixed nonlinearity like ReLU, we opt for a parametric ReLU, where this slope on the left-hand side can be chosen by the network. And this allows it to choose between being highly nonlinear and actually completely linear. And thus the network can easily select how isometry preserving it wants to be. All right. So we have figured out this cool way of increasing the throughput in neural networks, which can also be combined with classic approaches such as quantization. But now let's think about a different use case, one which was not possible with the previous approaches for increasing the efficiency of the network. So let's consider some smartwatch which monitors the human body function to assess general health of the user. Now, due to battery constraints, you'll need highly efficient processing. So you may want to opt for a small network. But if the prediction about patient health is highly uncertain, you may want to switch to a more expensive network to be really sure that the patient is not gonna have some heart attack or something. So the watch should be able to switch to a more accurate model if necessary. Now, unfortunately, you have big memory constraints in watches, and you may not be able to store, or you don't want to store multiple models and clutter up all the space. So what our approach is going to enable is we're going to be able to have a single model that can run at 3 different speeds, or even more if you want to, which all have their own trade-offs. You can either have the fast mode, which is less accurate, the normal mode, which is more accurate, or even the slow mode, which is much more accurate. And this can be all done in a single network. You won't need to load model weights from the memory and back, and you can instantaneously configure between them. It's absolutely no overhead. Now, how are we going to do that? Well, we essentially partition the protected subspaces that we have as we want. In particular, if we wish higher accuracy for the cat query, let's say, we can just get rid of the dog query and enter the cat query twice. And then after unbinding, we can average the resulting vector. And thus we essentially have an ensemble method embedded into a single neural network, which we can choose at any time as we wish. So this partitioning can be switched around at inference. Okay, so let's recap the blueprint for a successful MIMAconf. Firstly, we adopt a residual network structure. Then we use a regularization of the convolution layer to make them more asymmetric. We use a parametric value as our activation function instead of the normal value. And we adopt a high network width to get into this overparameterized regime, which also allows us additionally to have less interference between quasi-orthogonal vectors or between bound or protected vectors. And lastly, the first and last layers are applied in separation. Well, the first layer is applied separately because we want to increase the width of the network, and the last layer is applied separately as a cleanup operation. Let's talk a bit about some empirical results then. Well, we're going to look at Cypher 10 and Cypher 100 and MNIST. We weren't able to consider ImageNet because of licensing issues. Now, our baseline is going to be a wide ResNet with 28 layers of consecutive CNN layers, which has 10 times channel width of the normal ResNet. Wide ResNets are actually state-of-the-art for CNNs on Cypher 10 and Cypher 100, and as such, they were a natural fit in any case. Now let's consider the accuracy that we get on Cypher 10. Here with n equals 1, n equals 2, and n equals 4, we denote the speedup that we get, which is proportional to the number of superposition channels. And as you can see, we get a consistent accuracy drop, which is bigger for Cypher 100 due to Cypher 100 being a more difficult data set and the network needing more highly nonlinear maps to be able to construct the necessary function. And as such, you have a more interference between the channels. Now, what's super exciting is that a single dynamic model actually performs very similarly to the static ones that we just considered now. This is a single model that has 4 protected channels, but in the case of the gray box, we put in 4 different inputs. In the case of the blue box, we put in 4 times the same input. And in the case of the orange box, we have 2 inputs, which we distribute across these 4 channels. Now, it's important to note that this network was only trained on the case n equals 1 and n equals 4. So the case n equals 2, it has never seen during training. And it's actually quite surprising that we still get such a low drop. And if you train with this case as well, you could even reduce this drop further. Now, what's very exciting about this graph is that the drop of the case n equals 1 is very small. And that means that whereas previously you just trained for the n equals 1 case normally, and you have this one network which can just compute one image at a time, now with barely any accuracy drop, you can have a model that is able to compute about as accurately as the normal model in the slow case. But if you want to, you can just run it 4 times as quickly with a negligible accuracy drop. So we sort of have a free lunch situation almost. Okay, to put our work into a bit more perspective, we compare against Datamux. Now, Datamux was really like the pioneer of computing in superposition. It was the first work in 2022 which considers computing in superposition in neural networks. Now, as you can see, our accuracy scales much better as the number of superpositions increases in the network. Datamux proposed binding each input. Well, they didn't call it binding because they didn't use the vector symbolic architecture background, but they proposed binding each input via its own 2-layer CNN, which in the case of MNIST outputs then 8 feature maps or channels. And this output, they just superposed in this 8-dimensional space, which led to high interference in their case. So additionally to the fact that they don't scale quite as well as us in terms of accuracy, the reduction in max in operations is much less pronounced. We get about an 11x reduction, while they get about an 1.3x reduction. And this can be attributed to the fact that they use this overbloated binding operation, as well as the fact that they also need to train 4 different of these 2-layer CNNs to bind. So the whole thing is much more complicated. Whereas with our method, we have like this principled VSA approach giving better results. We're going to come back to Datamax later on when we discuss transformers. Now, there's a bunch of interesting stuff that I want to show you. Firstly, if we train the network for more epochs, all different modes, static modes, improve. But what's even more interesting is that the difference, the gap, essentially, when you switch to higher superpositions, it decreases. Now, this can be attributed to the fact that the optimization problem of having multiple inputs being put through the network is much more difficult than if you have just one input. So you need longer to converge to a good solution, meaning that if we throw in more compute at it, we may be able to decrease the drop further. Also, we can push our superpositions up to a factor of 10x with a predictable drop in accuracy, more or less. At some point, at like 8, 9, 10x superpositions, we get less stable or less reliable convergence during training, which then leads to the network being more or less accurate on the holdout test set. So that means that if you really go to like these high superposition regimes, you need to have a good optimization procedure, or you may need to train it to compete multiple times and just pick the best one. Whereas for low superpositions, there's not this big variance. Okay, so let's switch gears and look at transformers. Transformers, well, the MLP part of transformers is pretty straightforward. That's not so complicated. But the attention part really needs a new mathematical approach if we want to compute there also in superposition. Now, in transformers, the output tokens are produced as a weighted sum of these attention values times the values of the token embedding. Now, these attention scores are just the exponential in the product. If you normalize it, it's actually just a softmax between query key alignments. Now, we will disregard the softmax normalization just to simplify the exposition. And we also want to care about like these factors of maybe square dimensionality in the exponential to make it all a bit more neater. So let's think about the trivial approach, where we just have the keys, the queries, everything in superposition as we did before. And let's look at what happens with attention. Well, if the keys and the queries are in the protected subspaces, then if we apply bilinearity in the product, we get these 4 terms where the cross alignments are cancelled. So that's great. But still, you get, as an output of our attention score, you essentially get the multiplication of the attention scores that we want of the separate sequences. Now, this is an issue because attention scores are not like high-dimensional vectors where you may be able to then take apart and retrieve information of the individual inputs that were combined. No, it's a scalar. And from a scalar, you cannot retrieve 2 scalars. There's just not enough information in there. So this fails. We have irreversibly multiplied the attention scores, significantly blurring attention. Now, Datamax essentially does that. They don't discuss it, but they get to this framework, which when we run it on the data sets of associative recall and induction heads, which are important data sets to test your capabilities for attention, you completely fail. Here the networks, they have exactly the same number of parameters, but still you're not able to perform at associative recall induction head. Now, these two data sets are not unimportant. They're quite useful, or they have been shown to really assess capabilities for language modeling. And induction head in particular is even being, there's a bunch of work that examines the process of induction heads, which believes that induction head is the primary component in natural language modeling, which enables our modern transformers. So induction head essentially has like this weird symbol, which is like this perpendicular symbol rotated to the side at some point in the past, and then at the end, you just have to like find the token that followed this induction head. And you can maybe think about that if you like if you have a conversation with some chatbots and you want to refer to something that happened in the past, then induction head is useful because it sort of can retrieve what followed from the past depending on your question, maybe, which can sort of get back this information from your conversation. And associative recall is similar. It has like these value key pairs. Essentially, you're encoding a dictionary in the past. And then you just look at the last token. And from that token, which is key, you want to retrieve the value that belongs to it. Now, how are we going to tackle this issue of this irreversible multiplication of attention scores? How do we get around that? Well, we don't build on normal transformers, but instead on linear transformers. Now, linear transformers have their own motivation, irrespective of our computing in superposition. Linear transformers were introduced, and they're called linear, because instead of the normal transformers requiring a quadratic computational complexity in the sequence length, because each query and each key have to attend to each other, they enjoy a linear complexity in the sequence length, and thus they can be scaled to much longer sequences. Now, linear transformers use this inverse kernel trick. Essentially, they realize that the softmax kernel, the exponential of this key query alignment, can be written as an inner product in an infinitely dimensional space. And they approximate it with an inner product in a finite dimensional space. Now, this expression here, if you just compute this phi of kj with phi of qi and you apply this, you get to the same expression for transformers that we just had a few slides in the past. Now, what's nice with this explicit inner product is that we can use associativity of matrix multiplication to factor this bracketed matrix, which we're going to call matrix A. Now, with this factoring, you actually get to linear complexity, which I'm going to explain just in a second. So to analyze the complexity, we're going to assume that our key query and values are in d-dimensional Euclidean space, and that the feature transformation map into r-dimensional space. So if r goes to infinity, we get exact approximation of this, or we converge exactly this exponential in the product. Now, naturally, because the matrix A is a sum of a bunch of outer products, it's going to have dimensionality of d cross r. Let's think about the complexity of constructing this output. Well, applying phi costs OLDR, because we have to do it for each token position, and the input is d-dimensional and the output is r-dimensional. And under the hood, essentially what it's doing, you have a matrix multiplication of size d cross r, followed by some nonlinearity. So that's why you get to OLDR. The outer product also costs OLDR, because we need L different, we look at L different positions, and it's a d-dimensional vector outer product with an r-dimensional vector. Now, this product with the transformed queries also costs OLDR, because we have to do it for each query with always the same matrix A. And it's just matrix vector multiplication if you think it through, you just get dr complexity for each query, transformed query. So in total, we get to OLDR, whereas the normal transformer gives us OL squared D, because you have an inner product between each pairs. So if R is much smaller than L, R is maybe chosen like 200 or something, then you get much better scaling. Okay, so now let's try to make this into, build this into a, try to adjust it such that we can compute in superposition. Well, what we're gonna get, as you're gonna see shortly, is that for n squared protected channels, we only get n as a speedup. So we only get the square root of speedup in terms of the number of protected channels that we use. And so as a minimal working example, to see that we get a speedup, we're gonna need some square larger than 1. So we're gonna go with 4 different channels, color-coded with red, orange, green, and blue. And just to remind you, only the keys and the queries of the same color are gonna align with each other, are not gonna be vanishing in the product. Okay, so this is the main object that we're gonna look at right now. And it looks really intimidating, but we're gonna try to unpack it step by step. So we're gonna have a superposition of pairs of values, keys, and queries from different protected channels. Now, it's important to notice here that in this bracketed stuff, which is going to become our A matrix, all 4 colors occur. And the pairs of colors of values and keys are always the same. So we first have red, orange, and then we have green, blue. On the other hand, on the right-hand side, not all colors occur. Only red and green occur. And the red and green are chosen such that only in these outer products, we have 2 outer products on the left-hand side, always only 1 term matches. So we couldn't use red and orange, or we couldn't use green and blue. In that case, the algorithm does not work. So why did we choose it this way? Well, let's apply the distributive property of matrix multiplication and use the fact that we approximate the exponential in the product with this feature map phi. Now, as you can see in this expansion in the product, only 1 color matches, first red and then green. So we're going to be left with this term because all the others cancel. And now, if we expand this, we just get the desired output of the tension of the red channel as well as the green channel, together with some noise in the orange channel and the blue channel, because the orange values and the blue values are multiplied by the wrong weights. So that's just going to be noise. We're going to neglect that. Now, if you want to have the outputs on all 4 channels, on also orange and blue, we need to repeat this with queries from orange and blue. But it's important to notice that this A matrix that we have on the left-hand side is the same. We can construct it once and reuse it twice. Okay, let's think about the computational costs that we get with that. Well, let's recall the computation costs that we had previously. We had like all those OLDR operations for the feature map transformation, for the outer product, and the matrix multiplication that we have there with the X. Okay. So once again, expensive is going to be the feature transformation, the outer product, and the matrix multiplication. So compared to previously, we need to evaluate our feature transformation twice in this A matrix. And we need to compute twice the outer product, which for our working example, where our speedup hopefully is going to be n equals 2, it's just going to increase the cost by n, by the square root of the number of superposition channels. Now, the multiplication with this phi vector is also going to double in cost. We're going to have to evaluate this feature map twice for the different pairs, and we're going to have to evaluate the matrix multiplication twice. So it's going to also increase the cost by factor n. Additionally, you're going to have to add the values, the keys, and the queries. which is going to cost OL n squared d, but this is going to be negligible. This is going to be much less than the other terms, as you're going to see in the O notation in a second. Okay, so whereas previously for n squared different inputs, we'd need a cost of OL dr times n squared with the linear transformer. Now we have OL n dr plus ln squared d. So this ln dr only has one n compared to previously, so we get a speed up in the square root of the number of superposition channels. And this term to the right is going to be negligible because r is much larger than n. R is like in the hundreds. So we can cancel that as well. Okay, so it all works out with the computation analysis. And trust me, you cannot get rid of this superposition in the A matrix, and you cannot apply only phi once. You need to really have this combination of both applying the phi multiple times and having this A matrix of different superpositions. Okay, so let's look at the architectural diagram of the MIMO former. What we're going to have here is, different to previously, at intermediate stages, we're also always going to have our 4 different protected channels separately. We're not going to keep the superposition alive for the whole network. We're going to start with those 4 different channels separately, and we're going to apply the linear layers to them to get the value key and queries of these token embeddings. We're going to bind them to compute our A matrix, which is then going to be a single object. And we're going to bind and superpose our queries before applying this feature transformation to then have these 2 different transformed queries. We're going to apply them to the A matrix to get 2 different outputs, which each have a superposition of also 2 outputs. And that way we get to our 4 outputs essentially. But in each of those arrows, there are 2 outputs plus noise. Then, if we have multi-head attention, we're going to concatenate and apply a linear layer to combine the heads as is usually done. For the residual connection, we also now need to go down from these 4 different superpositions to only 2. So we're going to bind our token embeddings and superpose them accordingly to how they're superposed in the outputs of like one of these 2 arrows. Then we can either unbind directly and run it through the multi-layer perceptron on all 4 separately, or as shown here, we can run these 2 superpositions with multi-layer perceptron and unbind at the output. Now, because we have much more binding and unbinding operations than previously, we opted for a much cheaper VSA framework than HR, and we went for the map with the bipolar key representation, where the binding operation is just a Hadamard product with these 1s or -1s, and the unbinding as well, where the keys are frozen because they're not differentiable. Now, how do we fare empirically? Well, as you can see here, in contrast to Datamux, we're actually able to compute associative recall induction heads and get very close to the performance that the usual transformer has. Also, on the long-range arena, you can see that we get accuracy drops that do not explode. They're quite consistent as well. It's interesting to note here that the deep transformers fare more poorly, both in the baseline case of n equals 1, as well as how they scale. Because in deep models, you always need to bind and unbind, and that can increase, of course, the noise that we introduce. Because with each attention layer, we have like this additional 2 noise vectors that due to these residuals in the attention. Wide models here just refer to models that are not quite as deep, but have much more attention layers and possibly larger MLPs. Okay, so you may still be worried about the cost of our binding and unbinding operation, but as you can see here, in terms of the total percentage, they're super small. They don't really cross 0.14% of the total cost. Here on the left-hand side, you can see the case of speed up of n equals 2 or n equals 4, either only speeding up the attention layer or both attention and MLP, depending on where we do the unbinding. As you can see, we can get the accuracy much lower. So our method doesn't really have a significant overhead. The main issue that we did not look at in this work, which we sort of forgot, was that we apply our binding method after projecting the keys, queries, and values. If we did that previously, we could already project in superposition and get also speedups in the projections. Initially, we did not consider that projections make up such a large part of the cost of a transformer. And then we already had like a bunch of compute costs that we threw at it, so we kept it at that. Okay. So in summary, MyMonets are applicable to many deep neural network architectures, among them CNNs and transformers, as we have shown. MyMonets can run dynamic inference, which is this really cool way of embedding an ensemble method into a single network and instantaneously on-demand switching between our accuracy throughput operating points. Our MIMO-former, in contrast to previous work, does not blur attention scores. So we're the first work that's able to compute in superposition and attention without completely destroying the properties of attention. Finally, we provide our code on GitHub. And that was it. Thank you for listening. Now we get to the discussion part. I'd be happy to answer any lingering questions that you may have.
Nicolas, thank you very much. Great talk. Fantastic. So now it's time for questions. Please unmute yourself and speak up if you have commands or questions to Nicolas.
Hi, I have a small question about something quite early in the talk, where you mentioned that this binds a value with multiple keys and average error results to increase accuracy. Are you able to talk a bit more about this this part of the capability and what assumptions go into this? What's needed to achieve this? Because obviously it's not true for all scenarios. And later you talk about switching from HRR to map. So if you're able to expand a bit on that. Thank you.
I did not catch the first part of the question. There's a lot of background noise. So about the binding something in the first part of the talk, I think. But I didn't really get much more than that. I'm sorry. Did anybody else get it or hear it?
My attention was a bit blurred. But my attention scores were blurred a little bit. Adam, if you can type your question into chat, because it was really noisy.
Yeah.
I mean, I cut only every second word. Maybe we can move on. I had a question on my own. When you show the degradation in performance with the number of channels that you superimpose, I wondered if you consider it playing around with dimensionalities. I mean, was it kind of design choice to fix dimensionality to certain value?
You mean in the CNN transformer?
Yes, in this CNN case.
Actually, so the dimensionality is quite important of the binding. Well, we went quite quickly. We went with this position-wise HR binding, which already immediately showed much better performance than previous attempts. I think IBM attempted previously to also bind with like convolutions and stuff, which were just pretty expensive for what you got out of it. So we quite quickly went to this position-wise HR binding. We also consider actually binding with matrices, also with embeds, at each position separately. It was the performance was essentially the same. It was just more expensive. So we quickly went to this HR position-wise binding. But then we realized that we were in this very low dimensional space. So from that on, we already thought, well, let's first apply the first layer to increase our dimensionality where we actually perform our binding. And there we tried out a bunch of ResNet architecture. And we showed that the total width of the network was pretty substantial to the performance. I think I also have a graph here. So this is for 2x throughput. And you can see here, this first value, 4, 8, 10, 12, indicates how we scale the total width of the network globally, whereas the 2, 4, 4, 4 indicates how we scale the first layer output. And as you can see, the accuracy in Cipher 10 is sort of all right for different sizes, but in Cipher 100, it's really important to go to these really wide networks. To some degree, this also holds for the case n equals 1, which is why the CNNs for Cipher 10 and Cipher 100s that are state-of-the-art are all wide ResNets. But we noticed that the drop in accuracy that you get when you superpose, when you compute in superposition, is more pronounced than the drop in accuracy that you get when you don't compute in superposition, when you decrease the width. So the width is much more important when you compute in superposition than normally. So, which means that this is really only well applicable to neural networks that have like this high over-parameterized regime, which I guess nowadays many do. I mean, transformers are huge, for instance. They have like these 12,000 dimensional spaces where they put their embedding vectors, which gives a lot of room to actually compute in superposition.
Yeah, thank you. That's what I wanted to ask.
Maybe I can also answer, there was a question in the chat, or maybe a remark, about the general idea of training a neural, I'm just going to read it. By the way, the general idea of training a neural network on superposition of bindings was described in the work of Brian Chung, Superposition of Many Models into One, at NeurIPS 2019, for the purpose of avoiding catastrophic forgetting in neural networks. Yes, we read this paper right at the beginning of the work, and they were, to some degree, an inspiration for us. But what they did is they superposed the weights of the networks to have multiple models in one, but they only applied one input. We sort of do the opposite. We have multiple inputs, but one set of weights, whereas they sort of encode a multiple set of weights in the network, but then access them with different inputs. Yeah.
Yep. All right, let's see if anybody else. Adam.
Is this better?
Oh, yes, absolutely.
All right. All right. Yeah, thanks. Thanks for the talk, Nicolas. So give me 1 second to reformulate the question. At some point in the beginning of your talk, you asked about or you shared that you can reuse layers for the same value. So instead of pairing multiple values with each with their own key, you can pair one value with multiple keys to boost the accuracy in that category, right? And obviously, there are a few assumptions that go into this. This is not true for any paradigm or any superposition. And later, you also talk about HRRs and transitioning to map. And I wonder, like, what went into this? How did you see this vary? And then, secondly, on that point, does this improve the robustness of the CNN, which is classically a problem? And you indeed briefly mentioned that this approach is quite robust, but I would like to see this in the perspective with the multiple binding regime. Thank you.
Okay. So you're referring to this slide, I think, where we apply dynamic inference.
Correct.
Basically, we had like this multiple different inputs. Well, I don't think there's that many assumptions here to be able to switch from this one to that one. The important part is that here, maybe you could argue that the images might already be to some degree orthogonal. They might to some degree be orthogonal from the get-go, and then with binding, they might be even more orthogonal. Whereas here, they're sort of exactly the same. And then we really have to hope that they become orthogonal just through the binding with the key. Now, as far as I know, this is quite a universal property of vector symbolic architecture.
Sure, I was not talking about that, but to the increase in accuracy of superposing with different keys and then averaging back again. Thank you.
So, okay. I guess the accuracy here, this delta is negative. So it's slightly lower than if you only compute with one and you train only for one. So you are a bit lower than if you just compute with one. Essentially, the way I see it, you make up for the fact that you compute in superposition by then averaging through an ensemble method. And I mean, important for that is, of course, that's, well, you're in high-dimensional space such that this computing superposition works in the first place. So you need this model to work in order to be able to run dynamic inference. But then once you have that this method works and that your binding is well enough that it works equally well whether you have the same images or different ones, which requires a high-dimensional space, then this one kind of follows suit quite directly. I don't think there's that many assumptions that additionally go into this compared to what you have here. But what you get is you just get, you essentially are able to come up for the additional loss in accuracy due to computing in superposition by averaging at the output and using this ensemble method. Ensemble methods are in general always higher in accuracy than the single one because you have a better generalization and you can have like this majority voting stuff going on. So it's really it just shows that the trade-off seems to be going well in practice, that you can almost make up for ensembling with what you lost by computing in superposition. Does that answer your question, or we can discuss more if you?
Yeah, no, that does answer the first part of my question, I think. And then the second part was about how this influences robustness of the network, especially against adversarial noise.
We did not do any analysis on adversarial attacks, but that would be a very interesting follow-up work, of course. But yeah, I suppose it should be more robust because we're having an ensemble method. But that, yeah, of course, that would need to be analyzed thoroughly as well. Thanks for the question.
All right, so we have Dennis who raised his hand first, and then Ross.
Yeah, thanks for the presentation, Nicolas. I was curious about the CNN part, because you had to do a number of modifications for the whole thing to work. And is there like, do you have any intuition for like which modifications are the most crucial ones? And because it's like, it seems that you eventually have the interplay between like trainability of your network and the fact that the superposition works. And of course, maybe, you know, some things might actually affect the training performance, but they improve, you know, the superposition and kind of vice versa.
It's a great question. So we always work with ResNets, because if you switch from ResNets to, I guess, non-ResNets, in the case of CNN, the accuracy just drops in the baseline by so much that we didn't really want to consider these cases. But the question whether this asymmetry regularization or the nonlinearities are more important is quite interesting. So the regularization is very important, and I have also results that show that. Let me just grab them for a second. This one. You can see that in the case of Cypher 100, that the black one has no orthogonal regularization. But then, once you just add a little bit of regularization, you already have a big jump in accuracy. And then if you regularize too much, you get a drop in accuracy. So this is quite significant. The choice of activation function is not quite as significant. Where is this slide? I don't see it right now, but oh no, it's here. Yeah. So yeah, as you can see here, it's really close. There's no very clear winner, but we still kept it as part of our blueprint because because of the theoretical properties that we get more modeling flexibility. And there's actually an interesting analysis that comes with it. If you look at the slope that we get for these different superposition values, and here you can see they all start off at 0.5, which is like maybe some standard very linear case. And as you can see, in the case of no superpositions, we actually get even in this non-monotonic, no, in this regime where it kind of looks like an absolute value function. Whereas if we have a bunch of superpositions, we remain in this highly linear part. So it's quite interesting to already look at the analysis there. And you can really see the network kind of doing this trade-off, even if at the end we sort of get the same performance for this particular use case. You can also go with different activation functions, such as a shifted ReLU, and you observe the same behavior. And also, if you compare Cypher 10 and Cypher 100, you see that Cypher 100 becomes more nonlinear, whereas Cypher 10 is sort of more in this linear regime where it keeps the larger part of the network in the linear part, which really goes to show that this trade-off happens in the model. We also tried an additional thing, which I didn't mention in the presentation, which was skip init and Dirac init, where you initialize the skip connection, or where you initialize this residual connection to 0. And there we didn't really get that much of a change. Actually, if we didn't use this, we got the best performance. But yeah, there's like these bunch of different architectural choices, which in some cases work better or worse. But I think it's really cool that you can at least also like analyze it and look at the weights, and you kind of see this trade-off happening live. But to recap, really the most important architectural design choice there, apart from the whole binding and choice of binding and like applying the first layer separately and the last one, is really this regularization term, which makes a big difference. Yeah.
Got it. Thanks a lot for this elaborated answer.
No worries. Thanks for asking.
You're muted again.
Ross, sorry, I was muted.
Yeah, Nicolas, thanks very much for that. Just a quick suggestion. Could you go back to slide 20, please?
Yes.
Yeah, and this is sort of carrying on as from what Adam was asking. Yeah, just looking at that, that reminds me of some work I did with Simon Levy in 2009 in our analogical mapping. I mean, so in the case where you've got multiple copies of the same input going in, so the same, say, the cat on each of the legs of that calculation there, and effectively the result you're seeing is that, you know, if you put more copies through, you get, you know, better averaging out of the noise. We did a similar thing in the analogical mapping paper where we had a cleanup operation, but where we effectively had multiple replicates of the same data, but where we were applied different random permutations to each of them, and then did the calculation and then averaged the results together. So essentially, we had we'd chosen, if we were using your diagram here, 3 different random permutations to apply to the replicates of the same data. And then at the output end, instead of unbinding, we had the inverses those 3 permutations. So as an alternative to using binding to doing those keys, you might want to consider looking at different random permutations of the data instead.
I did not actually look at permutation as, I guess permutation to some degree you can consider it as a binding operation as far as.
Yeah, absolutely. Yeah. So I mean, the choice of the permutation is equivalent to your choice of the key in the binding.
I mean, I guess a random permutation is part. I mean, it's a subset of our binding method. It's cheaper, much cheaper. But since we do convolutional binding, we just compute the convolution with the key, with a convolution between the key and the value. If our key is just a Dirac delta at some point, we get permutation in this along these channels. So I guess your permutation approach is a subset of the HRR binding.
Yeah, no, I just thought it might be of interest as a if the computational costs are sufficiently different, then it might be worthwhile doing that instead of the binding. Yeah.
Yes, I guess we could have. I mean, here the nice thing about this binding operation is it's differentiable. We can just learn the keys, which is super important for the binding part, for the unbinding part. I guess for the binding part, it wouldn't have mattered. As we have shown, we can just use a random key there as well. So in the case of like these deep neural networks that we use, the binding completely vanishes. Like it doesn't matter at all. The unbinding is a bit more relevant because we use complete matrix, which of course costs much more, L squared instead of L log L of the binding. But yes, so I guess for the later part, for the transformer, it would have been quite interesting to also look there at different binding methods. Right now we just used this map thing, these bipolar keys. And here, I guess some permutation would have also been interesting with, I guess, pretty much the same cost. But I guess what also would have been interesting to look at a bit more closely would be having some sort of differentiable binding, because right now it's quite difficult for the network to actually achieve this mapping, because it sort of has to align everything. Like it cannot, for instance, in this something I forgot, I didn't mention, is that because we have multi-head attention, we have a different set of binding keys here than we have here in this skip connection. So essentially, the network, in our case, also has to learn how to adapt the binding that we apply to the values in this superposition, how to change it with this linear layer such that it works well with this different binding that we applied. And that's not trivially given. So, but it's a necessity to have two different bindings because we have a different dimensionality.
Yeah.
So I guess what would be quite interesting here is to also switch to some sort of differentiable binding mechanism, which still is fairly cheap. Maybe something like what's this called again? Fourier HR, like this binding with complex numbers of units.
FHRR. I mean, yeah, that's essentially that's Hadamard product, but where you're using complex values instead. So you're just using phase.
Yeah, but it's differentiable, right? You can choose the phase.
Yeah. I mean, for the bindings with the keys, given that they're fixed, if you're using permutations instead, given that they're fixed permutations, although randomly chosen in the first instance, would that actually make them effectively invisible to the differentiation?
Given that they're fixed, yeah.
Yeah, I mean, because they're constant. It's you're not learning anything. It's it's just part of the hardware.
Yeah, yeah. But still, I mean, I guess if we, in this case here, if we have two different binding keys, the network would, two different permutations, the network would still need to be able to somehow like match them, I guess. So, I mean, there's it's a huge playground. I mean, we only looked at a very small subset of VSA architectures, but I'm sure that there's a huge potential to also try out different stuff here, and permutations certainly would be another interesting approach, especially because it's super hardware efficient.
Yep. Okay, thank you very much. Thanks.
Thank you.
So we have one question from Adam.
In the chat.
Wait, Adam, wait a second. So let me, it was hidden by another window, I mean the chat window. So
Did
let me
I
see.
first answer the chat, or?
Yeah, please go on.
Okay, so the question is the programmable nonlinearity a new contribution, or do you have a link to the paper that introduced that? I don't have a link on top of my head, but I have a good description where you can easily find it, because this parametric ReLU was introduced, I think, by Kaimang He, who also introduced I think, the ResNet, which was the first architecture that outperformed humans on ImageNet. So this nonlinearity here, I think, was introduced together with some analysis of initialization of deep neural networks, such that the variance of the size of the either forward or backward pass does not blow up. And there they showed that this parametric ReLU, it's called parametric ReLU, but the paper is called something differently. I don't have it on top of my mind. There they showed that this parametric ReLU actually leads to better performance in the base case, which here we do not observe, but I guess it depends on the exact use case. And this other shifted ReLU was used, which I showed here at the end of the talk at some point. Where was it? Here. This one was used by a paper called, I think, ISONET, which got around using batch normalization and residual connection by regularizing the networks to be isometric, which is also where we got the regularization term from. And this is a special case of, I think, something called flexible ReLU, which is, I think, a paper FReLU. Yeah. Hope that answers your question in the chat.
So did you have another question, Adam? Since it was your question.
Yeah, it's more of an outlook question. So if anyone else has another question.
Then we have a comment from Josh. The permutations are just linear transformations, so you should still enjoy differentiability as with binding, right?
Yes, it's the whole network is still differentiable, but the permutations themselves are not, because the permutation is a discrete operation. You choose how far you shift the whole input, and this is not differentiable because it jumps from one permutation to the next one. There are differentiable permutations, but these, if you do not threshold it, they result in a matrix multiplication which is dense, and hence you no longer have the computational savings, I guess. Hope that answers the question.
Okay, we go back to Adam.
All right, sure. So you of course zoomed into convolutional neural networks and the equivariances that you want to maintain there. And in hyperdimensional computing, one of my major interests is that you can model apparently any topology in hyperdimensional space and do this quite natively. And there are a few ways to do this even. But just if you could elaborate a bit more on on how you see this scaling from convolutional neural networks to something like geometric deep learning, where you can have different topologies you work on, be it graphs or three-dimensional space or some parameters that are cyclic, etc. Thank you.
That's a really good question. I guess the important part is that if you have graph neural networks, there must be permutation invariant in terms of the graph nodes. So if there you apply, similarly to us, this position-wise HOR to each, or some other position-wise operation to binding operation to each node representation separately, then once again you get this translation equivariance in the case of graphs. Now, in the case of other topologies, I mean, you always have to look at the symmetries, at the group symmetries that you have there. But I think the main recipe is that you always want to have some binding operation that is translation equivariant with respect to the symmetry of the domain if you want to keep this through the network. Because the binding is part of the network. You need to, if the rest of the network has some equivariance property, then the binding operation also needs this equivariance property. Additionally, as said here, you also need to consider some other maybe locality assumptions. In graph neural networks, I guess it depends on which model you use, but many of them only have finite many hops to other nodes that you include at each layer. So also there, you may not want to spread the information across all different nodes, because then you no longer have this locality. But in the case of graph neural networks, it's actually very similar to here, because you can just apply your binding operation to each position separately. Now, I guess the downside to having this position-wise HOR or any sort of binding operation that agrees with this translation equivariance is that you lose the high-dimensional nature, because I guess a graph representation you get, as for a graph representation, you get like a huge feature vector if you consider all the different features at the different graph nodes, if you start off with some features. But as soon as you switch to this position-wise binding operation, your effective size becomes much, much smaller. So yeah, I guess the name of the game is to find the largest possible binding operation that agrees with both your group invariance or equivariance of your domain, as well as with some locality assumptions, because you just have finite compute. But we actually did not consider any different geometric deep learning frameworks in our work. So this was more of on top of my head, just trying to embed geometric deep learning into.
That's what I was aiming at. Thanks.
Okay. I look now at my clock, so time is running fast, and we have a very lively discussion here. So, but I think it's time to wrap it up for today. So I would like to thank you once again, Nicolas, for the great talk and the fantastic discussion that it initiated. So, and thank you once again for joining. So I see you in 2 weeks from now on the next VSAONLINE. So thank you, and see you next time.
Thank you. Thank you. I was
Thank you. Bye.
excited that I could be here.
Bye.
Bye, guys. Bye.